All right, good morning, everyone. I'm Kentaro Nagamine from Osaka University in Japan. We're the only two Japanese participants in the workshop, but in addition to Yuichi, who is off on Monday. I'll do my best here. Great to see all friends, and thanks to the organizers for this opportunity. And I'd like to talk about this topic, about anomalous abundance ratio and topic of MF. Maybe I was originally scheduled on Monday talk, but I had to teach on Tuesday morning, so I was only able to make it here on Tuesday. Calling kindly rescheduling for this session. Okay, so here are some of my PhD students in Japan, Osaka, and also some collaborators from the Empress team at Tokyo University. Okay, so we've seen this nice picture from Galaxies yesterday on Monday as well, maybe a few times. And this firefly sparkle is showing in this lens system, redshift 8. Some alter detections and pink star clusters have been identified with cell masses similar to the globular clusters. And they also show this nebula-dominated spectra, which suggests very high electron temperature, so also maybe a hint of popular MF. And this idea is collecting very significant tension lately from IG sources. You also see in this image from camera 23, also showing a very high nitrogen to oxygen ratio for this GNZ11, there's 11 source here, relative to the local H2 regions, and also as well as galaxies. And the similar diagram for this same nitrogen oxygen ratio as a function of metallicity. The same region here is the camera 23 region. On the bottom, you see here the same data point as here. And then here, we're showing this Nomoto 13 regular track of the yield model with noise unit stars. At late times, you can achieve this observed level of NFO, but at early time, at low metallicity, you're not able to reproduce that with noise. If you add AGB contribution, we can explain some of these data points at intermediate redshift range, and also as well as regular Wolf-Rayet type stars with the wind and supernova from many 06 models can also account for this data point. However, some of these upper part of data points is very difficult to explain with regular yield models. And here's another estimate for the GNZ11 from the Sobe 23. And there are also some hints from the globular cluster sources in the local sources. Also seems to suggest these very anomalous abundance ratio. So this is also very interesting to compare against the JWC sources. So these authors here actually involve some exotic models of Wolf-Rayet stars with dark collapse. Some of the high mass stars, about 25 solar mass or so, may collapse into dark objects like black holes. Therefore, they don't eject and pollute the initial enrichment. Therefore, maybe they can account for this enhanced nitrogen ratio. Also, Tominaga, Umeda have also another models of Wolf-Rayet stars with strong winds, also trying to account for this enhanced level. That's the motivation. And also lately, Sobe 23 also looked at some of the JWT sources. They also show a very high enhanced nitrogen ratio of oxygen. And that again brings some interesting IG sources for top-level MF. You can also turn your eyes to the local dwarf galaxies, trying to look at these as analogs of the primordial galaxy. And that's what this Empress project is doing, searching for this low stellar mass, less than 7 solar mass galaxy with elevated specific star formation rate here on the bottom, and slightly lower metallicity below 10 solar metallicity galaxy, as shown here. We have a handful of already very good spectra, and one additional twist to these sources is that you can estimate the helium abundance of these sources from the local NTGs. And in addition to this, combined with these local dwarf galaxies, and added these data points from the Empress NTGs, we can do regression fit, and this intercept at zero metallicity can tell you about the primordial helium abundance, which allows you to compare with primordial big bang nuclear synthesis field. And this value is in comparison to the Planck estimate of this big bang nuclear synthesis. There may be some tension with other estimates here. So this result also is attracting a lot of attention from the cosmologists who are interested in exotic big bang models. So motivated by these sort of indirect evidence of top-level MF at high redshift, we're performing some of the Bloom simulations with this 7K Fukushima We're trying to focus on this redshift 10 galaxy in the beginning. Here are some images of the nice large spiral galaxies at redshift 10. We're using Gadget 3 Osaka code with developed in our group over the past couple of years with the regular star formation models, supernova feedback model, similar to the super bubble feedback models, cellular chemical evolution models for species, gradual cooling, updated space formulation, and unique background, etc., all tested in the context of the Agora project, which Joe, I think, will talk about on Friday. The initial run we did with Nomoto 13 yields, but we quickly realized that we need to consider other yield models as I showed earlier. Here's initial results from that run. There's a stellar mass, star formation rate, metallicity, and alpha enhancement here. Okay, so two of these runs, we also use this Limongi Sheffi Ikini model to account for this elevated enhancement of some of the elements. And both models can account for the stellar mass as being together very nicely at redshift 11. Star formation rate also looks very good, but metallicity we actually overpredict a little bit compared to this estimate. There's also new data for the redshift 14 source called GS14, 0 and 1. For this source, we require this elongated CFD model to account for that mass. Star formation rate is pretty good. And the virtue of having simulation like this is that we can look at the spatial distribution of these elements. And here we see evidence of enhancement, spatial segregation of these initial enhancements of these some of the elements. And here we're plotting this helium-enhanced outflow gas because you need this enhancement to occur only in the primordial enriched gas without being polluted by the subsequent oxygen enrichment by the later star formation. So if you can start to resolve these distribution of elements with the high-resolution images, it would be nice to see more evidence of this. And enhancement is much weaker in the regular Nomoto yields. You have to have some of these special yield models to account for these enhancements. When compared to this Matsumoto data that I showed earlier for the primordial helium abundance, this is the observed linear regression result. Our pixel-based analysis of the simulated galaxy lies on this color gradient here, which is much shallower compared to this current observation estimate. Redshift 0, this is the input primordial helium abundance, but it's very difficult to actually account for the high helium abundance at the very low metallicity because these galaxies quickly get enriched by oxygen, so that these data points quickly move towards the right, and it's very difficult to fill this part of the diagram. Same thing has been shown with this latest paper by Yanagisawa 24. They use the same software set which they use to analyze local dwarf galaxies for the JLSD. They also show these data points very highly elevated relative to local dwarf galaxies and also the Empress local galaxies, and these seem to show also the elevated helium abundance. So summarizing all of that, regular Nomoto yields cannot reproduce this even the local data points at ranges. Limongi also can account for the local HQ regions and local dwarf galaxies, but these high Z super enhanced data points by the JLSC is very difficult. So ISOBE 23 is bringing out postulating some of these exotic Wolf-Rayet models or tidal disruption events, supermassive stars, which can enhance this nearby ISM with its rich maybe required. And the important point is this fast rotating massive stars contribute maybe significantly to these elements, like carbon, nitrogen, oxygen. In this interior, there's several convective zones that appear as a time over here, which requires rapid rotation. So here's an example of 60 solar mass model, and this convection actually brings out this element that was produced by CNO cycle toward the surface and then get ejected to account for these enhanced elements. So this is an example of 60 solar mass rotating objects, but also 3,000 solar mass model, similar to the supermassive stars at high redshift. They also show similar behavior of multiple convection zones, enhancing enrichment of nearby SMs. So this is an update by Nando 2324. on top of this original Nomoto calculations of 9. It's a type of view. Okay, so we're trying to also do more realistic accounting for the dwarf galaxy evolution using similar codes that now updated to Gadget 4, Osaka, and 3. We're performing sets of zoom runs to simulate the dwarf galaxies. And here are some preliminary results highlighting the variation due to the feedback models. Some feedback models can account for this high path track from the stellar mass evolution versus 10 to 0. Some other stronger feedback models can get suppressed from stellar mass evolution. They grow very rapidly at the very late time, so there's these very strong variations and very tricky to analyze. But we're able to produce the Empress-like low metallicity galaxies at redshift 0 also. We're also trying to highlight the differences between the canonical IMF, Chabris IMF, versus the top IMF. Also shows these variations over here at the low mass level. So these evolutions are coupled effect of both supernova feedback model variations as well as the IMF variations as well. So difficult and distant panels. Okay, at the last part of my talk, I'd like to highlight this crocodile simulation set that we have been performing. This is another PhD student that we had in Osaka, Yuri Oku, just graduated now a postdoc at Zhejiang University and with Raymond Chen. This is also the Gadget 4 Osaka code with transformation and super feedback with agent feedback and with background. Yuri actually gave a talk presenting earlier part of this model maybe 2 years ago at this workshop. Then we also evolved this model to incorporate the Tigris, Kima Ostraika ISM simulation results to account for this metal loading that Mark Strumholz actually discussed this morning very nicely. We also try to account for this top heavy IMF and low metallicities in these models, given this recent simulation data from UCSC. And then also the standard chemical evolution using the same package as standard 3 code, variety feedback models. So we produce these sets of simulation varying these feedback models to see the impact of this different treatment and also contributing to the CAMELS project. We call it crocodile simulation because this mascot over here is actually the official mascot of Osaka University in Japan. We call it Dr. Wani. Wani in Japanese means crocodile. So it's also the official mascot of Osaka University and also Tanaka City. So if you come to Osaka and go to the University Museum, you'll see this full-scale skeleton of the crocodile, and that's the origin of this acronym name. And here's some evidence of the excavation back in the day when they built a campus in this Tanaka City. The photo of the excavation and this whole skeleton came up, and so there's this academic name of this crocodile. The crocodile did exist in Japan also, at early time, prehistoric time. So here's also the result of this Oku's crocodile simulation. We input this top heavy IMF from the Chong 22. This is sort of the first simulation motivated model of the IMF. So it's a real dense cloud collapse simulations at early time. So they actually model this in terms of this F massive parameter, characterizing the fraction of the massive star fraction at very high mass range. It is the IMF. And depending on this parameter, we can actually tune how much fraction of the high mass contribution you want. And if you raise this contribution of top edge IMF, this specific energy input from the supernova or massive stars actually rises towards higher redshift as metallicity goes down. So this evolutionary impact of top heavy IMF is considered in the cosmological contest as a function of metallicity and also the high resolution ISM simulation. Even these stronger feedback at high redshift and low metallicity, we actually suppress the star formation quite a bit at high redshift. Therefore, we actually underpredict the redshift 6 galaxy stellar mass function. And if you don't have any feedback, more consistently with the feedback-free scenario of Abishai, we actually can account for the data, honestly. At lower redshift, at redshift 0.1, similarly to other simulations like Eagle, Illustrious, we actually nicely suppress the low mass end with our feedback model, and then slice of over prediction high mass end, but we do agree with the observed local galaxy experiment as well. one thing we think we're doing better than the other simulation is the baryon fraction, which is very important for the CGM and IGM observation. So here's a plot of baryon fraction, the function of halo mass. This is the Eagle run result, this is the TNG result, and our data points over here for some of the models. This is some observational data, observed range over here. So that's something we think we want to analyze more in terms of CGM physics, IGM physics. And we're preparing this website for the crocodile simulations here set release. So you can go to this website, also the QR code. We plan to make it public, available, so on request. So please try to analyze it if you like and utilize it. And the nice thing about our simulation series is that we have these variations of different treatment of feedback. So we can try to constrain feedback recipes, and also the relative contribution between supernova and AGN can also be addressed by contrasting these models. Okay? There's a press release purpose image, not physically so accurate, but shows the evolution from high Z to low Z, evolution of massive structure. Okay. So here's my quick summary of the talk. We see the enhanced element of helium and nitrogen, observed in high Z and also at the local EMPG, both at high Z and low Z. So our simulations show enhanced helium abundance for selective regions in the earliest unpolluted ejecta through the contribution from the rapidly rotating massive stars. But yet, there are also data points even higher helium and nitrogen abundance at low metallicities. These are very difficult to explain. So regular Nomoto 13 cannot account for these super enhanced element abundance. So some of the data points can be accounted for by the Monge-Chaffee models. Does it better, but even higher data points exist. So we need more contribution from rotating massive stars, and EOS for helium and nitrogen super enhancement is necessary, as suggested by these so I introduced this new simulation set, and one final thing is that I have been discussing with Joel and Avishai and others about a possibility of having a workshop next year in Osaka. So just a few months ago, we had a Agora in Asia version conference. And this year, Agora is actually put into the online format next week. But if people are interested, I can try to host similar workshop, the Agora in Asia, 2 days at the end, but maybe 3 days in front of that. We can have a similar workshop like this in Osaka. So we're contemplating 2 weeks in May. So the second week or the fourth week of May. If you're interested in coming to Japan next May, check this URL and the QR code, and then let me know which one's better, and then I'll try to reserve the venue, and then we'll go ahead with the conference. All right, thank you very much.
Fantastic. For some of these high nitrogen-rich, exceptionally high nitrogen-rich galaxies, we have spectra with quality high enough that we can start to constrain iron abundance, which also seems to be fairly high. But I didn't get whether you can, is problematic or you need a separate channel. Well, I see depends a lot on the yield that they...
Right, there's one panel here from this Limongi and also Nomoto. They do actually show the enhancement of iron as well. We haven't done very careful comparisons with those data points. In the paper, we will show more comparison with based on one zone model calculation between these varied yield models, see how much enhancement you get.
Why is iron so much discrepant with respect? Because the others are more or less consistent, but iron is...
Well, no, there are no data points here.
I mean the yields, why are so dramatic?
So this Limongi model, we took this so-called set R in their paper, which have a dark collapse above 1025 mass. So every high mass star actually going to dark collapse without ejecting any matter. That's why you can get very large enhancement really early.
What if you include very massive stars, thousands or tens of thousands or so?
Yeah.
An argument for such stars is that you need some way of quick starting the growth of supermassive black holes, because we're starting to see the very massive ones at high redshift. How would those affect the yields?
Right. So that's their demonstration here. The 3,000 solar mass model, right? And I don't know about 10,000 solar mass star, like supermassive star model. That's what the survey is also invoking. So any of those models that can show these enhancements through this enhanced convective zone would do the job. But as these papers show, right, how do they affect? Well, so that really depends on the hydrodynamics of the cell evolution, and that's very tricky. Depends on how the gases are accreted onto these stars, what happens on the surface of the stars, when do these really go off as supernova. All of that really matters, and it's a very tricky, I think, calculation to be done. So these calculations actually do not go, it just stops at the very end of the explosion, right before explosion. So I think more hydrodynamic calculations with realistic conditions of inflow and interior of the stars need to be done with various stellar mass.
Time for one more question if we want. Okay. Yeah, then the recording won't pick it up, so.
How do the yields from this model compare to you showed at the very beginning? Wolf-Rayet stars could explain the nitrogen abundances.
Right. We haven't done the SSP calculation based on these yield models yet, so I don't have the plot to show that. But here's an example on this diagram of O. So they do account for these cracks in some of these enhanced level regions. So I imagine they would do this equally good job as some of the enhanced models of Wolf-Rayet.
All right, let's thank Ken once more.
Thank you very much.